So the information linkage we concerned is in a system or procedure where there exist some secret variables inside that is designed to be hidden from unauthorized users. However, your implementation may typically include some unexpected information flows that will transfer partial information about your secret to some attacker-observable variables. And to worst, the attacker could control some attacker-controlled variables inside the procedure to maximize the linkage by infer the different parts of your secret information by changing your attacker-controlled variables. And based on such information linkage model, there are a lot of practical attack vectors. For example, if you use the web query traffic analysis, you could review the query content through the package sites. If you use a crime attack, you could infer the cookie secret by inject some contents to the request and observe the compression ratio. And if you use there is also the off-path TCP sequence number attack that can review your TCP state by send the spoofed packet and observe the TCP-related profile to review the linkage. And there are so many different attack vectors. And the question we want to solve is whether we could build a general framework to evaluate the information linkage no matter what kind of attack vector you use. The most related work is quantitative information flows. This technique usually will use the entropy-based uncertainty about the secret to depict your information linkage. However, there are several limitations using this technique. First, this technique usually suffer from expensive computations when they try to calculate the entropy, especially when they try to calculate the conditional probabilities per observable variables. Typically, they will use either brute force enumerations to calculate this probability or use the counter that is only feasible to linear constraints. The second limitation for this technique is that they typically will use entropy-based measures to depict the linkage, which will usually mix the linkage pattern into one metric, because the developers may want to understand linkage in different aspects. They may try to know how often the secret will be linked and how much info is linked about the secret. For example, you may have a procedure that directly returns the secret values, so both dimensions will be maximized. And you may also have procedure that tell you whether or not the secret is even or odd. For this procedure, only one dimension will be maximized, but another dimension is not that high. You may also have procedure that will review the complete secret value only when the secret is even. And for those three different procedures, they link information linkage in different ways, in different patterns. If you use entropy-based measures, they will mix those patterns into one metric. So to solve those challenges, we propose a new framework to help developers to understand the information linkage. By first extract out a logical post condition about the procedure using symbolic tuition, and then feed this post condition to an approximate model counting to quantify the interference. And finally, we will use the quantified interference to summarize the information linkage about your procedure. To motivate you about how to use quantified interference to understand the information linkage, I will first introduce a very simple attack task. That is, attacker try to differentiate whether the secret is a value S or S prime by inject some attacker-controlled variable and observe attacker-observable variables. And both controllable and observable variables will compose attacker's views about this computation. And the attacker could completely distinguish whether the secret is S or S prime if these two views are completely different. If attacker's views are completely overlap with each other, then the attacker could know nothing about whether a secret is S or S prime. The most interesting case is when the attacker's views are partially overlapped with each other, then only yes or no answer to whether the attacker could distinguish whether it's S or S prime is not enough. And we propose to use the J-car distance between two attacker's views to depict how easy the attacker could distinguish whether a secret is S or S prime. However, only quantify such interference between two secret values is not enough to depict information linkage, because distinguishing between two secret values does not reveal how much information can be revealed about a secret. If you consider a procedure that directly returns whether a secret is even or odd, for this procedure, the probability that you could distinguish between two different values are pretty high, but the amount of information that's revealed through this procedure is pretty small. So we think it's necessary to not only quantify the interference from one value, it's also necessary to quantify the interference from many secret values. Thus, we redefine the Ziqiao distance measurement by considering the interference between two secret sets. The only difference from a previous definition is that the attacker's views will be the views from many secret values instead of just one secret. And as for the implementation part, if you want to use the Ziqiao distance to estimate the interference, we should not only consider the Ziqiao distance between two particular secret sets. We need to consider the average Ziqiao distance per secret set size n. And however, there are a lot of challenges to estimate the average Ziqiao distance. First, there are so many different secret sets for each size n, and we cannot enumerate all of them because it's pretty expensive. The solution we propose here is that we could randomly and fairly choose a sample of secret set to depict the average Ziqiao distance. Then the following question is how to fairly and randomly choose a secret set. The naive idea is you could pick the secret value one by one for many times. However, this is expensive when your secret set size is pretty large. And to solve this problem, we utilize the property of universal hashing, which will map the secret domain into many buckets. And by choosing one bucket, you choose a subset of secret from the domain. And if we repeat this sample selection process for many times, we could guarantee the expected size of the sample is the secret size divided by the number of buckets. The final question to calculate the value for a Ziqiao distance is how to calculate the different components in your Ziqiao distance equation. For example, we need to calculate the size for the conjunction set and disjunction set. And to provide a concrete idea about how to calculate these things, I will provide a concrete example how to calculate the conjunction set size here. So the purple block here represents the domain for the attacker's view, which composed with the attacker-controlled variable and attacker-observable variable. And the block labeled with 1 represents the solutions that belongs to the conjunction set, while the block labeled with 0 represents the solution outside of the conjunction set. So the task here is to calculate how many blocks are labeled with 1 here. If you enumerate all of them one by one, it should be expensive. So we will apply a very similar hash technique that will map the CO domain into many buckets. And by choosing one of the buckets, we choose a sample of CO values. Then the only task we need to do is to count how many blocks within these blue samples are labeled with 1 using a looped SAT solver. And for this example, there are 3 blocks labeled with 1 within the blue sample. So we could finally estimate the conjunction set size should be 3 times 2 equals to 6. That's because the number of buckets we use are 2. And by repeat such process for many times and change the number of buckets we used, we could tune in the confidence about the estimation and the precision for the estimation. And after we quantify the interference, we could define a new measurement to depict how often and how much information will be linked. If you recall the motivation example, we know that the Ziqiao distance with small secret set size will be more sensitive to how often the secret can be linked, while the Ziqiao distance with large n will be more sensitive to how much information is revealed. So we could first define a threshold for the Ziqiao distance, and then use the minimum secret set size n that make your Ziqiao distance reach the threshold to represent how often the secret info be linked. And use the maximum secret size n that make Ziqiao distance to reach the threshold to represent how much info is linked. And to be more standardized to compare different implementations, we will normalize the minimum n and maximum n to eta min and eta max values that range from 0 to 1. And finally, we will use the average eta min and eta max among different thresholds to represent how often the info will be linked and how much information is reviewed. And to provide you a more intuitive idea about how we could use our quantified interference to depict the information linkage, I will present dummy examples here. So for these procedures, it will directly return the secret values if the secret is divisible by a constant value m. To evaluate the information linkage about this procedure, we will first quantify the interference using a Ziqiao distance curve for different secret set size. And then we will summarize the eta min, eta max measurement to depict the information linkage. And if you look at this procedure, you'll know that when we increase the constant m, the amount of information, the number of secrets that can be completely linked will be reduced. That is consistent with this observation that the Ziqiao distance will be decreased when you increase m. And such reduction will be more obviously when the secret set size is small. And if we map this Ziqiao distance curve to the eta min, eta max figures, you will find that the eta min, which represents how often the info links, will decrease when you increase constant value m, while the eta max, which represents how much information is reviewed, will always be pretty high. Specifically, when you set the constant m equals to 1, then this procedure will directly return the secret for every secret. That means that it's consistent to our observation in the Ziqiao distance curve that every Ziqiao distance will be maximized. And if we map to the eta min and eta max, both eta min and eta max are 1, which is the maximum value. And if we increase the constant m to 64, then only 1 out of 64 secrets will be completely linked. That is consistent to this observation that the Ziqiao distance with small n is small, while the Ziqiao distance with large n is large. And if we map to the eta min and eta max, we will find that eta min is small, while the eta max is still pretty high. In our paper, we also do the case studies on the real code basis under attack we mentioned before. The first code base we evaluated is a search engine called Sphinx. We evaluate its linkage in the autocomplete features and compare different padding strategies to see whether our measurement could evaluate the difference between different mitigations. The second code base we evaluated is a compression algorithm under the crime attack. We compare different compression algorithms, and we conclude that the adaptive compression algorithm is more vulnerable than fixed dictionary compression algorithm. The final code base we evaluated is a complex TCP implementation in Linux kernel, and we compare the original design with the design with different paddings designed by ourselves. And we could observe different security level by padding different patches to the TCP implementation. As a conclusion, we propose a new framework to quantify the interference. And using this quantified interference, we could understand the information linkage in different dimensions. And we implement this framework in a very scalable way using hash-based model counting. And finally, we'll use experimental results to show the effectiveness of our measurement using both dummy examples and real code bases. Thank you.
All right, come up for questions. You guys make me sad. All right, so I have a very simple question. So in your case studies, like, can you actually look at different like program points and say like, okay, it's exactly at this point where I'm leaking this amount of information, or is it at the end of the day like, hey, you're with like the adaptive, you're leaking this much, with the not adaptive, you're leaking this much? Like, how can we learn from this to build better systems?
Yeah, currently we do not locate the exact point in your program to see whether that's a point of a linkage, because typically the linkage is composed from different points of your program, right? So we currently try only quantify how often the linkage happens and how much information can be reviewed. And but since we use the solver to find the feasible solutions in your program, we could provide some examples for you to tell in what kind of examples you will break the non-interference property to guide the developer to find a way to fix this.
Got it. Okay. Other questions? If not, I have another question. So where does it break down, I guess? So you looked at real things. Did anything besides those like ones that you mentioned, did it like break apart at some point where you couldn't quantify because you're doing the static analysis?
You mean how to break down the program into different components?
No, I mean like, was there a case where it just did not work?
Oh, your network, yeah. So for that network cases, we evaluate the search engine itself, the software itself, because the package is composed by the application level, in the application level. So we only need to observe whether in application level protocol, the package size can infer the content.
Okay, yeah, we'll talk more about that. All right, other questions? Sad audience. All right, well, if there are no other questions, let's thank her again.